Okay, good day to all of you. Now we are all set to start a new chapter, that is work, power, energy. Okay, previously we have completed a laws of motion. So Newton's three laws of motion. Okay, first law which gives us a condition of equilibrium. Second law gives us acceleration. Third law gives a action reaction pairs, active reactive forces. And important concept we have studied, that is a free body diagram. So this is again a continuation of the kinetics, whatever we have deal with the in the laws of motion. Okay, kinetics and kinematics. Again, I am saying kinematics is, yes, it is a relationship between displacement, velocity, and acceleration without considering its cause, that is force. But kinetics is deals with these all velocity, displacement, acceleration. But additionally, it deals with the cause, nothing but forces. So this work, power, and energy, this is again a continuation of the, yes, it is a continuation of the laws of motion. That is nothing but, we can say, truly speaking, continuation of the kinetics. This is nothing but the kinetics. So every time again we have to deal with the velocity, displacement, etc. But one important difference is what? In Newton's second law of motion, we have calculated acceleration. And from from acceleration, using kinematical equations, v is equal to u plus at, v square equal to u square plus 2s, or s equal to ut plus half at square. Using these three kinematic equations, we can calculate displacement, velocity, time, and all things. But in this, we have to calculate first, displacement or velocity, because a work energy theorem, which we'll study in, which will come in a due lecture. Okay, so this gives us what? This gives us a work done is equal to change in kinetic energy. So there is a relationship between, yes, work done and kinetic energy. And kinematical data, as per concerned with the kinematical data, you have to deal with the displacement and velocity. And from this displacement velocity, you can easily calculate acceleration. So nothing but roughly, if you divide these things, so in Newton's law of motion or in laws of motion, mostly we deal with the acceleration. But in this work and energy, we have to deal with the displacement, velocity, and then further we can calculate, yes, acceleration using a kinematic equation. Again, there is a mixing of kinematics and kinetics in this work, power, and energy. So in first phase, we have to concentrate on how to get the work, what are the sign conventions of work, how to apply correctly sign convention for work, and where work is zero, where it is positive, where it is considered as negative. Then, yes, we have to deal with the two types of energies, kinetic energy and potential energy, and the relation between them, or we can say, yes, principle of conservation of mechanical energy. Little bit we have used in vertical circular motion, this concept, but now it is in detail in this chapter. And yes, obviously, naturally, power is there. Okay, so work is nothing but a product of force and displacement. Displacement should be in the direction of force. Energy is, yes, capacity to do work. And power is the rate of change of work done. That is, the work by time gives us power. So we have to deal with separately work, energy, and finally, in the final phase of the chapter, we have to deal with the power also. Okay, but most part contains work energy theorem or principle of conservation of mechanical energy. And there is another important concept which is very useful in physics, that is a conservative forces and non-conservative forces. So we have to differentiate these two forces so that we can apply everywhere a work energy theorem for all cases. Okay, if there is actually it is saying is what, when you deal with the conservative forces, then you can apply principle of mechanical energy, and when you deal with the all types of forces, so universal theorem is a work energy theorem. That is, a left hand side work done is taken, and at right side change in kinetic energy is taken. Actually, work and energy again have a same unit, that is a joule. Okay, this is work, power, and energy. So let us start with the small concept of, that is, work done, and how to apply a sign conventions to work done. And then Yes, subsequent examples MCQ as per our routine, how to calculate a work done for given. And very important and is that work done is a scalar product of force and displacement. So you have to recall here a scalar product from mathematics, or you can, I suggest, see a video of basic mathematics of scalar product before going to learn this chapter, because a scalar product of force and displacement is nothing but a work. So force is a vector, displacement is a vector. These two vectors, yes, gives us a work, another scalar quantity, and that is, it is called a dot product or scalar product. Okay, so let us start with the work done. Okay, let us explore about a work. बघा, आपण जनरल लाईफमध्ये आपण म्हणतो की आज मी खूप काम केलंय किंवा आज मी खूप अभ्यास केला, माझं खूप काम झालं. सो दीज थिंग्स, बट रिमेंबर दॅट इज नॉट अ वर्क इन फिजिक्स. इन फिजिक्स वर्क इज व्हेरी डिफरंट फ्रॉम दॅट. बरं, इवन बघा, मून इज मुव्हिंग अराउंड अर्थ, ओके, इन सर्क्युलर ऑर्बिट. बघा, तो समजा असं म्हणलं मूननी की मला खूप वर्क झालं, आय एम व्हेरी टायर्ड नाव. बट रिमेंबर, आपल्या फिजिक्सला जर विचारलं की व्हॉट इज अ वर्क डन बाय मून, आन्सर इज नो वर्क डन बाय मून. ओके, बघा, फिजिक्स असं काय म्हणतो, वर्क इज नॉट डन बाय मून, बिकॉज ॲज पर द फिजिक्स वर्क इज ओनली अ फोर्स and displacement product. But remember, force and displacement should be in one direction, always parallel to each other. Either may be opposite to each other, but or in the same direction. But remember, they should be parallel to each other. And in circular motion, what happens? A force is acting towards the center of circle, and whatever displacement is tangential to that, means perpendicular to that, in the direction of that, yes, v. So here displacement and force are perpendicular to each other, so there is no work done. Means the force and displacement should have either 0 degree in between them or 180 degree in between them. If the angle is 90 degree, there is no work done according to physics. So therefore moon has done no work according to physics. Okay, so there are number of examples आपण बघणार आहोत पुढे. पण आपण जरा थोडेसे डेफिनेशनला बघून घेऊयात. वेन अ फोर्स ॲक्ट्स अपॉन अन ऑब्जेक्ट टू कॉज अ डिस्प्लेसमेंट ऑफ द ऑब्जेक्ट, इट इज सेड दॅट वर्क वॉज डन अपॉन द ऑब्जेक्ट. ओके, म्हणजे बघा, आता आपण एखादी खूप हेवी बॉक्स आहे आणि त्याला आपण फोर्स अप्लाय करताय. येस, फोर्स इज नॉट झिरो, यू आर अप्लाइंग फोर्स. येस, यू आर व्हेरी ऑनेस्टली अप्लाइंग एव्हरी, येस, फ्रॉम एव्हरी मसल्स ऑफ युअर बॉडी यू आर अप्लाइंग अ फोर्स, बट देर इज अ नो डिस्प्लेसमेंट, हेन्स नो वर्क डन. As the displacement is 0, so force into displacement, force into 0, that becomes a 0. So in that case, work done becomes 0. And if you not applying any force, obviously work done is 0. म्हणजे बघा, आपण जर एखाद्या बॉडीवरती फोर्सच अप्लाय केला नाही तर वर्क डन होण्याचा प्रश्न नाही. आणि जर एखाद्या बॉडीला आपण फोर्स अप्लाय करून पण डिस्प्लेसमेंट होत नसेल, आपण त्याला डिस्प्लेस करू शकत नसेल, तर यू आर नॉट डुईंग एनी वर्क. मीन्स देअर शुड बी अ डिस्प्लेसमेंट बिकॉज ऑफ फोर्स. म्हणजे तुम्ही जर फोर्स अप्लाय केला आणि जर त्या बॉडीचं डिस्प्लेसमेंट झालं, बॉडी एका पोझिशनवरून दुसऱ्या पोझिशनला जर गेली, तेव्हाच आपण त्याला म्हणायचं वर्क डन इज, येस, हॅपन देअर, वर्क डन झालं असं म्हणता येते. सो दॅट्स वाय अ डेफिनेशन इज सच दॅट वेन अ फोर्स ॲक्ट्स अपॉन अन ऑब्जेक्ट टू कॉज अ डिस्प्लेसमेंट of the object, it is said that work was done upon the object. Or in other language, see, work is said to be done when a force applied to an object moves that object. So effect will be there. If there is no any movement of the object because of your force, so there is no work done. According to physics, the work done is very different in that case. So therefore force and displacement are very necessary. So work done may be 0 when in which cases imagine work done is 0. If force and displacement are perpendicular to each other, then there is no work done considered. So in that case, work done is 0. If force applied is 0, then work done is obviously 0. And if force is applied, but displacement not happened there, then also work done is 0. So in these three cases, work done will be 0. So work done may be a positive, work done may be a negative. Remember, work is a scalar quantity, so it has, yes, positive, negative direction. Because this positive, negative direction is depend upon for the total work done. You have to some work done and deal with the force and displacement. That's why you have to apply these things for the work done. Okay, so for a work energy theorem, the left part contains work done, and that particular left hand side of the equation, we have to deal with the sign conventions. Means what is a positive work done, what is a negative work done, and what is a actually zero work done, and how to apply their sign conventions. So first of all, remember a formula for that work done is nothing but force into displacement. Just आपण एक roughly बघूयात what is the formula of that and what is the unit of this work done. So force acts upon body, and when it moves, then work is done on the body, and this is the main crux of this work done definition. Okay, so let us move further about sign conventions and its formula. Okay, we can calculate a work by multiplying force by the movement of the object. Okay, that is W is equal to, we can say W is equal to force into displacement. Either you can take D or S, whatever as per the requirement. This is F into S. So when we kick a football, we are exerting an external force called F, and due to this what happens? The ball moves to a certain distance. So this disposition of ball from position A to any position B is nothing but a displacement. You know that displacement is what? Displacement is the shortest distance between initial position and final position. Okay, we have studied displacement is what? So that displacement multiply the force. This is nothing but this product gives a work. This work is said to be done and can be calculated as F into D, and that is why its unit becomes Newton meter. Okay, Newton meter, and which is yes given by a joule. So joule is also unit of the work, but probably work done is always expressed in Newton meter, and when we deal with the energies and all things, so that is also a joule. So unit of this work done is a Newton meter or joule. And always keep in mind the force and displacement should be parallel to each other. Okay, either angle is 0 or 180, either they exactly opposite to each other or in the same direction. That is the thing, but should be parallel to each other. Okay, by scalar product we can also elaborate about work. So now it is a simple thing. Work is force into displacement. Okay, आपण थोडंसं डिस्कशन करून घेऊयात what is a scalar product and how it is yes work is given by a scalar product. Okay, let us say you are having two vectors. Let us say this vector as a vector A, another vector is vector B, and if you want to calculate a scalar product of this, then what is, yes, recall that scalar A dot scalar B is always equal to A magnitude of A magnitude of B and cos of angle between them, that is cos theta. So altogether it is AB cos theta. बघा आता ह्या A आणि B मध्ये suppose one vector A is here, suppose it has this direction and vector B has this direction, and this angle in this case it is a 90 degree. Then what happens? So this product becomes dot, yes, A dot B. This becomes A B and cos of 90. So what becomes it? So cos of 90 becomes, yes, 0, and that is why it becomes 0 here. So in the same way, if you consider this as a force, this is a force and this is a displacement and having angle 90. So we get work done is equal to vector F dot vector S. Yes, that is given by F S cos theta. Again it becomes 0. And when this angle theta is 0, then cos of 0 is 1 there. And if this angle is 180, cos of 180, that gives a automatically minus sign to you. So cos of 180 is minus 1. In that way, cos 0 is 1. So this is nothing but a best example of scalar product. So work is, yes, work is a scalar product. Recalling that scalar or dot product of two vectors, any vectors A and B, is nothing but what? A product of the magnitudes of A and B and cosine of angle between them. And therefore we have written here, we can read right here AB cos theta. Okay, so it can be positive, negative or 0 depending upon, yes, value of theta. So whatever rules of the or properties of scalar product you can apply for work done. So this is a significance of scalar product in the for work done case. Okay, now moving to sign conventions, how to apply sign convention to the work done, or which work we have to consider positive, which work consider negative, and which work should be a zero. Okay, बघा हे हॉर्स आणि कार्टचं आपण एक्झाम्पल बघितलं. व्हॉट हॅपन्स हिअर? सो येस देर इज अ सम वर्क डन बिकॉज बघा आता ही मुवमेंट जर आपण याच्यावर काढली, सो मुवमेंट ऑफ डिस्प्लेसमेंट डायरेक्शन जर काढलंय, पण बघा दिस इज अ डायरेक्शन ऑफ डिस्प्लेसमेंट. येस, ओके. सो दिस हॉर्स पुल्स in this direction. Okay, direction of displacement इथे काढू आपण. This is a displacement direction. Yes, and this force F is applied. And बघा या रोड कडनं हे फ्रिक्शनल फोर्स मिळेल. आता कॉमन फ्रिक्शनल फोर्स घेऊ आपण दोन्हीसाठी. सो दिस फ्रिक्शनल फोर्स इज देअर, you know F well, mu k into R. Okay, so whatever its total weight, if you consider total weight here mg, okay, total weight mg, and a total, imagine a normal reaction, total normal reaction, suppose this is R. Okay, so these are the forces. बघा आपण forces कसे काढले? If you consider this body as a point mass, this force F, this force normal reaction, this is mg, and this force is a frictional force, that is mu k into R. Okay, so what is the direction of displacement is very important here. बघा तसंच नॉर्मली विचार केला तर F आणि ह्या जर विचार केला आपण, फोर्स F आणि S मध्ये अँगल किती आहे? Yes, theta is equal to 0 is this case. So this is a force F and this supposed displacement S. So it has angle 0 degree, and by yes dot product also it becomes 1. In these two forces, displacement direction बघा अशी आहे आणि फोर्स इकडे आहे. So this is the case of this 180 degree. In this case cos theta minus 1. But for normal reaction and this displacement, remember this normal reaction and displacement having angle 90 degree. So in that case cos theta becomes 0. So now easily you can recall what is the work done of force F. Okay, what is work done of force F? Work done of force F is work done is equal to, okay, mathematically also you will take Fs cos theta, if you take dot product Fs cos theta. So angle between force F and S is 0. So cos theta is 1. That's why it becomes directly only Fs. Okay. So work done by frictional force is what becomes work done by frictional force. Okay, this is work done by F. Okay, this is work done by mu k, etc. So this becomes Fs cos theta, but remember angle is 180 degree, so that is why this become minus S cos theta minus, so minus Fs, and work done by a normal reaction 0 because cos theta is 0, cos 90 is 0. Okay, cos 90 is 0, and work done by mg also, work done by mg also 0. So these are the positive, negative, or we can say 0 work. So normal reaction and weight doesn't contribute for work done. Only force F contribute positively in the work done. Mu k contribute for the work done but negatively. It opposes the proposed work done. बघा जो वर्क डन तुम्हाला करायचा होता because of force F. Okay, so that is yes opposes by a frictional force or any resisting force, always it is opposes. So it may be a air resistance. Okay, if you consider air resistance here, so that is also having the opposite direction of force F or displacement. So that is why yes work done by that resistance force also negative. बघा थोडंसं वेगळं अप्रोच बघा. when theta is less than 90 degree, okay, when theta is less than 90 degree, this is less than 90 degree, the work is positive. If force or direction of force is in the same direction of displacement, so work done by such force is positive. Okay, I am repeat this. A force or direction of force is in the same direction of displacement. Work done by such force is positive. If force or component of force is in the opposite direction of displacement, then work done is negative. So if theta is less than 90 degree, the work is positive. If theta is more than 90 degree, work is negative. And if is theta exactly 90 degree, then work is 0, remember. Then work is 0. Okay, so let us consider this again, one of the practical example to elaborate this, and then finally we can conclude about the sign conventions. I will give a list of sign convention possibly, so you can apply directly in the numericals. Okay, now consider one of the practical example of waiter and weightlifting. Okay, what? So check your knowledge of work done now. ओके बघा या एक्झाम्पलकडे आपण बघितलं इथे एक्झाम्पल ऑफ वेटर अँड वेट लिफ्टर. ओके बघा वेटर म्हणला की आपण खूप काम करून थकलोय तर फिजिक्स मानत नाही त्याला. फिजिक्स डज डिनाय इट बिकॉज फॉर फिजिक्स फोर्स अँड डिस्प्लेसमेंट शुड बी इन सेम डायरेक्शन ऑर यस पॅरल टू इच अदर, सो देर इज अ वर्क डन. बघा आपण जर ह्या वेटरकडे बघितलं तर काय दिसतंय, द डायरेक्शन ऑफ फोर्स इज दिस एफ. कुठला फोर्स आहे हा? बघा हा ट्रे आहे आपल्याकडे जो येणारा ऑर्डर घेऊन येतोय तो, and this is a tray, so force is applied by the by its hand in this direction, applied direction for holding purpose. Okay, maybe a reaction force, but direction see F and displacement matra yes ikde because he moving a forward direction. So this F and yes have 90 degree in between that. So in this case work done is zero. In this case work done is zero as force and displacement are having a 90 degree in between them, so work done is zero. But for weightlifter, see direction of force and yes, okay, direction of force and yes are here in the same direction, that is theta equal to 0. So when theta equal to 0, cos theta become 1, we know that this is theta 0. So in this case work done is positive because direction of displacement and direction of force, yes, work done is positive in this case and that is given by Fs. Okay, that is Fs. But here work done is 0. बघा असे कित्येक एक्झाम्पल आपलं घेता येतील. ओके, आपलं स्टेशन उतरल्यानंतर कुलीला आपण जर आपलं लगेज दिलं आणि त्यांनी डोक्यावर ठेवून जर जात असेल, सो ही मुव्हिंग फॉरवर्ड बट वॉट एव्हर फोर्स ऍक्टिंग yes in vertical direction. So force is vertical but displacement is forward, that is horizontal. So again he is not doing work according to physics. Okay, biologically, anatomically he is doing work, but remember according to physics he is not doing any work. For work to be done in physics, remember a force and displacement should be either in the same direction or exactly opposite direction. Then and then there is any contribution of work. It may be a positive work or it may be a negative work. If displacement and force having 90 degree in between them, there is no work according to physics work done. So these are. बघा आता आपण अगदी कन्क्लुजनला आल्यानंतर आपण एक एक्झाम्पल घेऊयात आणि हाऊ टू अप्लाय अ साइन कन्व्हेन्शन्स अँड हाऊ टू गेट अ टोटल वर्क डन ऑल्सो. सो दॅट इज जस्ट इंट्रोडक्टरी फॉर कमिंग फॉर वर्क एनर्जी थेरम. ओके बघा आता आपण साइन कन्व्हेन्शन शिकूयात फॉर दिस पर्टिक्युलर एक्झाम्पल. सपोज आता बघा हे आपली थोडीशी फॅमिलियर एक्झाम्पल घेतले मी. Suppose this force P displaces this body in this direction. Okay, in this direction, that is in the direction of P. This is the direction of suppose displacement. बघा साइन कन्व्हेन्शन्स वर्क डन साठी अप्लाय करताना सगळ्यात आधी डिसाइड करा व्हॉट इज द डायरेक्शन ऑफ प्रपोज डिस्प्लेसमेंट. देन यू कॅन डिसाइड साइन फॉर ईच फोर्स. बघा आता आपण विचार जर केला इथे, इफ यू कन्क्लूड दिस व्हॉट इज द डायरेक्शन ऑफ, सगळ्यात आधी कुठल्या फोर्स हे वर्क डन करतात. थिंक लाईक दॅट. स्टेप 1 इज व्हॉट, थिंक अबाउट अ डायरेक्शन ऑफ डिस्प्लेसमेंट. स्टेप 2 इज व्हॉट, विच फोर्सेस आर पॅरलल टू द डायरेक्शन ऑफ मोशन, विच फोर्सेस आर पॅरलल टू द डायरेक्शन ऑफ डिस्प्लेसमेंट. Okay, in this case force P around it, force P, frictional force and mg sin theta are parallel to a direction of motion, but this r and mg cos theta are not parallel, they are even perpendicular to the direction of displacement. So this r and mg cos theta doesn't contribute for work done. First eliminate these forces. Okay, step 1, decide direction of displacement or observe from the problem or given data, whatever. Then observe the forces which are parallel to, opposite in the same direction, nothing matter, but in the same direction, parallel direction, opposite or same direction, observe these forces. So in this case we have find force P and mg sin theta and what is this mu kr. सो आय हॅव कॅटेगरीज दीज फोर्सेस इन दीज फॉर्म्स. बघा याला मी काय केलंय, या पी फोर्स जो आहे ना त्याला मी काय म्हटलंय, अप्लाइड फोर्स. आय एम सेइंग इज अप्लाइड फोर्स. ओके, दिस इज अप्लाइड फोर्स. दिस इज फोर्स अप्लाइड एक्सटर्नली. Second category I have taken weight or weight component. Okay, mg or w, whatever, weight or weight component. Okay, and third force I am categorized as a resistance force, that is a frictional force. Okay, we can call it a frictional force, frictional or resistance force. Which force? The force which opposes, yes, proposed work done, that is I am calling them as a resistance force. So your forces will be categorized in these forms. There will be no fourth form. Okay, applied force, weight or weight component, and friction or resisting force. So remember, for applied force, but as per applied force is concerned, what is the sign convention for applied force? Remember, applied force साठी काय करायचं, if direction of force and direction of displacement in the same direction, so work done will be positive. Okay, work done, positive work done. If direction of displacement and force are opposite, just like this, then you have to consider work done as a negative work done. Okay, negative work done. This is about what you call it, yes, for applied force. म्हणजे बघा, अप्लाइड फोर्सची डायरेक्शन आणि डिस्प्लेसमेंट डायरेक्शन जर सेम असेल तर वर्क डन इज पॉझिटिव्ह. इफ अप्लाइड फोर्सची डायरेक्शन आणि डिस्प्लेसमेंटची डायरेक्शन जर अपोजिट असतील तर वर्क डन विल बी निगेटिव्ह. तुम्ही म्हणाले हे असं कसं शक्य आहे सर? येस, आय विल एक्सप्लेन इन ड्यू कोर्स हाऊ इट इज अपोजिट टू इच अदर ऑल्सो. ओके, सो लेट अस मूव फर्दर. Second case, that is about weight component. Okay, weight component. So I am yes, considering this, what if body moving upward, baga, if body moving upward, nothing but what you call it, against gravity, for weight component or weight I am saying. So sometimes weight is also in the direction of displacement or parallel to displacement. Okay, or weight component. In this case, weight component is there. Mg sin theta is a weight component. Okay, weight is mg, but here mg sin theta. बघा, आपण हँगिंग ब्लॉकच्या प्रॉब्लेम जर गेलं तर वेट जे आहे दॅट इज अ येस पॅरलल टू डायरेक्शन ऑफ डिस्प्लेसमेंट. दॅट्स वाय आय एम सेइंग युअर वेट और वेट कंपोनेंट. ओके, सो मूविंग अपवर्ड, सो दिस वर्क डन इज टेकन नेगेटिव्ह वर्क डन. ओके, if it is moving against gravity, remember like that, if it is moving against gravity, the work done will be negative. And if it is moving downward, so that work done taken positive work done. So in the direction of gravity, or work done in the direction of gravity, work done positive, against gravity negative. Remember like that. Remember, these you can't find in the books, etc. So that's why remember and learn it very carefully. So yes, there is no any problem for sign convention in further course. Okay, so third force is a frictional force. So it is clear cut, it is always opposes the work done. So work done by frictional force, work done by any resisting force, always negative. This is always negative work done. Okay, so I am concluding this. If for applied force, remember, if direction of applied force and direction of displacement same, work done positive. If direction of applied force and direction of displacement opposite to each other, yes, work done will be negative. For weight component is concerned, if body moving upward direction, work done will be negative. If body moving in downward direction, work done will be positive. And for frictional force, body moving upward, downward, rightward, leftward, doesn't matter. Always remember, work done by frictional force, work done by any resisting force is always negative. So let us apply these things for this problem. बघा, आता कुठल्या कुठल्या कॅटेगरी आहेत आपल्या लक्षात येतं इथं. सो यू आर हॅव्हिंग दिस फोर्स पी विच इज अ कॅटेगरी ऑफ अप्लाइड फोर्स. बघा, डिस्प्लेसमेंटचं डायरेक्शन अपवर्ड आहे, अप्लाइड फोर्सचं डायरेक्शन अपवर्ड आहे. सो वर्क डन, टोटल वर्क डन आपण म्हणू याला. ओके, समेशन ऑफ वर्क डन म्हणू शकता. सो दिस टोटल वर्क डन इज गिवन बाय लाईक दिस. ओके, यू कॅन गेट टोटल और सेपरेटली ऑल्सो. ओके, लेट अस कॅल्क्युलेट सेपरेटली फर्स्ट. फॉर पी बघा काय येणार आहे. सो आय एम टेकिंग पी. Yes, P into S. But I am taking positive, remember, because direction of applied force and displacement are in the same direction. Okay, second thing, mg sine theta. Body moving upward or downward? Ask yourself, body moving upward or downward? Yes, upward. So it is taken minus mg sine theta. This is a force into displacement, yes. So this is the work done. Now only friction remaining, that is always I am saying to you mu k into r into s. And we can take summation of this also, p into s minus mg sine theta into s minus mu k into r into s. Okay, so this is how to calculate a left hand side part of work energy theorem, a famous work energy theorem that we have to study. So this is how to apply a sign conventions for work done. So remember, okay, for applied force, for weight or weight component, and for frictional or any resisting force. This is simple logics you can apply, so you can do a problem yes, correctly. Okay, let us see some examples, discuss on the example and conclude this lecture. Okay, बघा आता पॉझिटिव्ह वर्क डन आणि निगेटिव्ह वर्क डनचा आपण एक्झाम्पलवर चर्चा केली थोडीशी. तर बघा, when body slides against a rough horizontal surface, its displacement is opposite to force of friction. So in that case force is negative. When body is going to slide against a rough horizontal surface, its displacement is opposite to a force of friction. So body going downward, so friction upward. So friction for friction is concerned, work done is always negative. Okay, when brakes are applied to a moving vehicle, suppose the work done by braking force is again negative because it all opposes the work done, because braking force and displacement are in opposite direction. In that case also a braking force, which is nothing but a resisting force, then work done again becomes a negative. When body is lifted, the work done by the gravitational force is also negative. Remember, body is lifted means displacement is upward direction, weight is downward direction. Again same story, but I have concluded this here. If body moving upward, so work done is negative in that case. Okay, so these are the some examples of. Similarly, see in case of if body moving in circular motion, what is the direction of force? Centripetal force. Yes, toward the center. And what is the direction of displacement? Yes, tangential to circular, means tangential and towards surface. What angle between them is? Yes, 0. So in that case, work done by a centripetal force is 0. Work done by centripetal force. Think on this. Work done by centripetal force is 0. When coolie walks on horizontal platform with a load on his head, he applies a force on it in the upward direction, so equal to its weight. So in that case also displacement is along horizontal direction and weight is along vertical direction. Again same story, work done becomes, in that case work done becomes 0. Okay, even imagine a simple pendulum case where tension in the string is along the string but displacement is perpendicular or tangential circular path. So again tension T and displacement having 90 degree in between them, again work done becomes 0. Okay, work done becomes 0 in that case also. Okay, these are a number of examples you can imagine that. Okay, when body falls under gravity, what happens? Gravity, displacement is downward, force is also downward, so displacement is positive, means weight or weight component I have separately told you. When a gas filled in a cylinder, okay, imagine a gas filled in the cylinder, a piston is there, movable piston is there. When gas is expanded, it applied force on the piston. Piston moving upward, gas is also applying a force, pressure force on upward direction. So in this case work done is positive because displacement and pressure force are in the same direction. When you stretch a spring, imagine this, when you stretch a spring, stretching force is in suppose right direction, so displacement also in right direction. So in that case also work done is positive. In that case also work done is positive. So all together conclusion is what? When applied for the concern with the applied force and displacement in the same direction, work done is positive. Applied force and displacement in opposite direction, work done is negative. For weight or weight component, always see what happens body. If body moving upward, work done is negative. If body moving downward, work done is positive. And for frictional force or any opposing, any resisting force, work done is always negative. Okay. So these are the basic sign conventions for work done. So apply this carefully to get out of this confusion in the sign conventions of work done. Okay, so let us conclude this lecture here. So let us solve some examples to elaborate this idea, but remember, careful about the sign conventions while applying a to the work done. So in this way, you have prepared the left hand side part of the work energy theorem. So remaining is only kinematics. The right hand side is the change in kinetic energy, that is as per the given data, final, initial, whatever it may be. Okay, let us stop here.